Okay, thank you for coming. I'm Yuta Tsuboy. Today I'm going to talk about data. Uh, I joined this company this July, and since then I have been working on a robot system which can communicate between humans in natural language. And we recently published a paper on arXiv, which the paper described a system, pick and place robot system, which which can handle natural language command. And in this project, we create a couple of data sets, and we realized how important data is again. So that's the motivation I want to talk about data in this presentation. So, can your learning algorithm be your baseline method, which can use 10 times more data than your method? Please raise your hand.
Yes.
Okay. So there's some. So I should stop here now. Okay, that's very interesting. There's several sample efficient method, but let me continue this talk more. But I think many of you agree data is important, and some people said data is king. And so the data is fuel of learning algorithm, and also the data advance. I mean, the good data advance research pretty much. So I compared the number of citation of ImageNet, a famous data set, with the number of citation of famous regularization method, Dropout. And as you can see, the number of citation of ImageNet is more than 9,000. That's pretty much a lot of over the number of citation of Dropout. So good data set advanced research. So I think that's so in academia data is also important. And in one article, I mean compare the average elapsed time between key major achievements such as spontaneous speech recognition between the key data set available, or the elapsed time between major achievement between major achievement and the key algorithm first proposed. And they found the algorithm is the average elapsed time between major achievement and the algorithm first proposed is like 80 years, but the elapsed time between achievement and data set is 3 years. So it means we already found some important algorithm already, but even that there is good algorithm. If there is not good data set, then it is not possible to achieve like a human level AI. So this is comparison is a little bit arguable, but anyway, I think that we can say there could be there could be algorithm which is already invented, but we don't have a good data right now, and if we could create good data, then we can achieve something new. And the importance of data is still remain in this deep learning era. So our research group found the performance still increase linearly with order of magnitude of trained data. So they create a much larger image data over ImageNet, and they found this trend is still continuing. And I have been talk about supervised data, and I like to categorize those data in two ways. So maybe first way was manual annotations, like segmented image or caption image or speech transcribed data. Those data are manually created. We have been using well-trained annotators before, but recently we use power of crowdsourcing to create a lot of data. And the second way can be logs of human or business activities. That's, for example, like a purchase record, or like search engine logs, or like a transaction between banks or private companies. Those are data that's also called as big data. And the good thing of this kind of data is naturally collected. I mean, people are not intentionally generate data. It's naturally generated by everyday human life or everyday business processes. So this could be I'd like to call this is second way. So I said the first and second, so maybe I should mention about third wave. I think the third wave could be self-play or self-supervised data. One example is AlphaGo Zero. So I think many of you know AlphaGo beat international Go champion, and but at that time AlphaGo was trained using human gameplay histories. But recently, Silva and other researchers found they can train AlphaGo without human play data. In AlphaGo Zero, they are trained by self-play. So it means so it's kind of adversarial training. So the system play against itself, and so automatically generate data by itself. So it's a pretty ideal situation because the system automatically generates data for their training. So that's ideal. And I think many researchers expected we can train Go system by self-play. But it took a long time. But because Go or this kind of game is easy to determine the game is success or failure. So, by nature, so it is easy to give a positive reward to action sequence which end with win, and we can give a negative reward or cost to the action sequence which ends with lose. So maybe this kind of self-play is not so easy to apply to the real-world task. But I found several similar research on other tasks. One is visual robot control. So in this work, they use more than 10 robots, and each robot doing try and error to pick up object. So with slightly different camera angle and slightly different object configuration. And by spend 2 months with this 10 more than 10 robots, they could collect more than million training data for robot grasping, and they found failure rate decrease linearly with order of magnitude of training data. So that's the same as image recognition case. So, so this is pretty good work, and I think the key point is how to determine the success or failure in this case. And in this paper, they use a heuristic to determine success or failure by using a state of robot. So if the robot hand is completely closed, so it means the robot could not pick up anything. So, and if the hand closed not completely, then it means we can say that the grasping is success. So by using this kind of heuristics, they could label automatically generated action sequence of robots. But the thing is, as you can imagine, that's not scalable. You know, it's not so easy to prepare like more than 100 robots right now. So there's an interesting line of work which try to leverage simulator to generate this kind of self-supervised data. So in this paper, they use more than 2,000 simulated robots to generate a synthetic pick and place experiment. The advantage of this approach is one is scalability, but another is we know this environment completely, so it's easy to determine the action, the task is successful or not. So that's another advantage. And also, when we train learning system, we need to determine hyperparameters, but it is easy to imagine, it is not easy to evaluate every model with different configuration by real robot. But if we use a simulator, then it's easy to evaluate each model, and we can select best model easily. The problem of simulation is there's a gap between synthetic world and real world. And in this paper, they tackle that problem by domain adaptation techniques. So, this one is a generated image which taken from the shoulder of robot. And this is a real image which taken in the real world. And we can imagine if, say, we use a CNN to recognize object in synthetic image, then maybe it's not so trivial to apply that CNN to real image. But they found if they create a realistic image generator, which try to fool adversarial discriminator, which try to classify adaptive image and real image, then we can train robot using a synthetic image. And the advantage of this work method is we can even easily add any random object which may not exist in real world, but we can try many tons of different shape of object and different color of object and different configuration of each object. So by doing this, they could achieve good grasp accuracy with mixed synthetic data and real image. So this is the conclusion. So as I said, I think everyone knows data is pretty important, and let's imagine there already could be key algorithm, but we need some good data to achieve your task. Then another thing is third way could be self-play and self-supervised data. I introduced the robotics case, but there is a similar work in natural language dialogue system. In that, agents communicate with each other. It's like a self-play, and learning how to negotiate each other. And the third point is simulator could be very important to exceed the limit of physical environment and make the learning scalable. Okay, that's the end of my talk. Thank you.
I remember that experiment where they had the line of robots, 20 robots doing the picking. That was 3 years ago, but okay, just thought it's only a year ago. Feels like it was longer ago. Has anything happened with that data since then? Are they able to apply it any other way?
Oh, actually, the next one is
same.
They are same group.
I thought it was Google, wasn't it?
Yeah, it's Google.
Okay.
So now they try to use synthetic data and combine with real data.
I see. So even after all that, they basically are trying to get more data. Okay.
But even Google, they gave up to increase the number of robots.
Okay.
Have you seen any example of using simulated data, but for the kinematics? Because this is task level data, no? Like the kinematics are not simulated because there is a lot of problems usually trying to really simulate the friction, inertia of systems. So have you seen any paper that it's applied more in the kinematics rather than the task level?
No. I just started this kind of work recently, so maybe other members from manufacturing may know. Sorry.
No.
Okay, so thank you very much.